Hi, everyone. My name is Yangye. I'm thrilled to be here today. Big thanks to Moov for the opportunity to share some thoughts on OPA. I'm an engineering manager at Torpago. We provide a spend management platform and more, purpose-built for branded business card programs offered by banks. I call myself a fintech goer because I enjoy programming in Go, and Go is literally right there in Torpago. Sometimes the universe just aligns perfectly, you know. I want to take you on a journey with us today. It's a story about breaking rules to build a better, faster, and smarter payment gateway. We'll start with the core challenge every fintech faces, making instant, perfect decisions when time is money. Next, we'll introduce our hero, Open Policy Agent, or OPA. You might know it from the world of infrastructure security, but we are using it in a way that might surprise you. Then we'll do a deep dive into our architecture. I'll show you how we combined OPA with our Go stack to build something both incredibly fast and flexible. Then the heart of this talk is about our secret sauce, the key patterns we developed to solve problems that felt impossible with traditional code. And finally, we'll wrap up with the lessons we've learned and a look at the future. Let me set the stage with a story that probably sounds familiar to many of you. So picture this. You're having a perfectly normal Wednesday, maybe thinking about lunch, when your phone buzzes with a message from one of your bank partners, and they say something like this: could you flag this as unusual and freeze card until a cardholder affirms purchase? It's a smart, reasonable request. They spotted a new fraud pattern and wanted to control spending at very specific high-end retail stores. But here's the thing. This request perfectly illustrates the challenge we face in real-time payment systems. Business logic changes at the speed of a chat message, but traditional systems change at the speed of, well, not chat messages. So what's the core problem? Speed versus complexity. On one side, you have speed. When you swipe your card, a clock starts ticking. We have less than 1 second to approve or deny that transaction. On the other side, you have complexity. That approve or decline decision isn't a simple yes or no. It's a maze of rules. We have to check the cardholder's credit, enforce their company's spending policy, check for fraud. All of this and more has to happen within that sub-second window. This leads to what we call the legacy trap. The traditional approach written in C# was to hard-code all this policy logic right into application. But this creates a monster. It was slow, it was risky, and it just couldn't keep up. Look at this C# code. Actually, don't look too closely because it might give you nightmares. Every new rule is another else-if statement. Every policy change requires a developer, a code review, a deployment pipeline, and some levels of approval, which might take weeks. Meanwhile, fraudsters don't wait 2 weeks. They are probably out there right now buying suspicious amounts of skincare products and athletic equipment. We realized that we needed to break some rules, specifically the rule that policy logic must be tightly coupled to application code. We had to get the policy out of the code, and that search for a better way led us straight to the Open Policy Agent. For those who haven't used it, what is OPA? The simplest way to think about it is as a policy engine. Your service asks OPA a question, and OPA gives you a decision back. That's it. It separates the thinking from the doing. OPA comes from the CNCF, the same foundation that manages projects like Kubernetes. Its whole purpose is to decouple policy decisions from your application code. The best part is that OPA doesn't care what you're asking about. It knows nothing about credit card or fintech. It just knows how to make decisions based on data. This flexibility is exactly what we needed. Rego is OPA's domain-specific language to write rules. So let's talk about rule and Rego. What is a rule? In OPA, rule is an if-then logic statement written in Rego. Every rule has two parts, a head and a body. The head is the decision it makes, and the body is the conditions that must be true to make it. The beauty is in how these conditions can be combined. If you need multiple conditions to be true, you just list them together. If you want to say condition A or condition B is true, you just write two separate rules with the same name. Think of it like this. If you have multiple ways to allow a transaction, you write multiple allow rules. If any one of them succeeds, the transaction is allowed. Let me show you how this looks in practice. Here's the simplest possible Rego rule. This rule just says allow is true if true is true. It always says yes. Use this in the real world, but it shows you the basic syntax. The package example line just gives our rules a namespace to keep them organized. The real power comes when we start using real data to drive these decisions. OPA supports two kinds of data sources, input and data. Getting this distinction is key. Input is a base document pushed synchronously to OPA, where data is the one loaded asynchronously. Think of it like a doctor diagnosing a patient. The input is the patient who just walked in the door. In our world, the input is the transaction that just arrived. The data is the doctor's medical textbook. It's all their reference knowledge. For us, data is the rule configs cached in memory. Let's see how we use the input document. First, we set a default. If nothing else is true, we deny the transaction. Here we have two rules. Our first rule says allow the transaction if the amount is less than $100. Our second rule says that allow if the merchant is a restaurant, using the standard industry MCC code for that. But what if we don't want to hard code that MCC? What if we want to look it up from our textbook? That's where data comes in. In this next example, the first rule is the same, but the second rule now checks against a whitelist that is part of our data. This means we can update the merchant category whitelist without touching the policy code. Our policy logic stays stable, but the data it uses is completely dynamic. This is how we keep up with the business. Our policies, just like code, also live in Git. They get reviewed in pull requests, and most importantly, they get tested. OPA has a fantastic built-in testing framework. The with keyword lets you mock both input and data without setting up a database or whatnot. You can create comprehensive test suites that validate policy's behavior against thousands of scenarios. Let me show you an example test. Here we are testing that our policy correctly denies a transaction at a discount store for $101. We use with input ads to create a fake transaction on the fly. The not allow is our assertion, checking that the policy says no, just like we expected. The test is completely self-contained, and runs in microseconds. When you run OPA test, you get detailed results showing exactly which rules were tested and how fast they executed. We have hundreds of these tests covering thousands of scenarios. This is what gives us the confidence to move fast. So to recap the benefits before we dive into our architecture, first, decoupling. OPA offloads all policy decisions. Our core service just asked the question. Second, readability. Rego is a declarative language that our business and the risk teams can actually read and understand. Now, let's look at how we put it all together. When a card is swiped, the authorization request comes from the card network, then an issuer processor, and finally hits our payment gateway, which is a Go server. The gateway's first job is to enrich the request. It pulls in extra data from our Postgres database. Then it hands the enriched request over to the open policy engine and asks for a decision. OPA runs through all the relevant rules and returns a decision, which our gateway then sends back to the card network. The whole thing happens in a flash. Let's zoom in and take a more detailed look at the data flow. First, the transaction just arrives. Second, our Go service enriches with more data, such as account balances and more. No decisions are made here yet. Third, the enriched data goes to OPA. This is where the magic happens. Fourth, OPA returns a decision, but not just a yes or no. It also includes rich metadata, such as risk scores and what actions to take. Lastly, if any other actions are needed, like sending an alert, those are fired off as events for other systems to handle asynchronously. Now, let's get into the patterns we developed to make this all work in the real world. To get this into production, we developed some key patterns. These are the secrets that made this project a success. First, we use OPA as a Go library, not a separate service. Second, we use metadata to create rich, actionable decisions. Third, we use cloud events to trigger asynchronous workflows. Fourth, we build a policy sandbox for zero-risk testing. Last but not least, we created a feedback system to make our policies smarter over time. Let's break this down. Starting with the decision we made, running OPA as a library. Our first and the most important decision was to run OPA as a Go library rather than a separate API service. This table shows why. First, evaluation speed. The Go library is faster because there's no network overhead. Second, language constraint. We're already a Go shop, so this wasn't a limitation. Security. We enable only what we needed. So no external API to secure. Lastly, deployment. We do have to update the entire service to change policies, but we've automated this. Here's what the actual Go code looks like. It's surprisingly clean. We have a function that takes a query string, some input struct, and returns a Boolean decision. OPA handles all the complexity of policy compilation and evaluation. We designed it to be generic so we can reuse it for all kinds of policies, from credit to fraud checks. The result is query evaluations that consistently take less than 1 millisecond. So we solved for speed, but our next problem is that a simple true or false from OPA isn't enough. If we decline a transaction, we need to know why. The answer was right inside OPA, using a feature called metadata. It lets you attach rich, structured information to any rule. Think of it like putting a sticky note on your decision. It has built-in annotations for title, description, and so on, so the rule becomes self-documenting. But more importantly, we can define custom annotations. We created a standard format for those sticky notes. Every decision comes with a tag, score, some actions to take, and so on. When a rule is triggered, our Go service doesn't just get back deny. It gets a rich JSON object with all of this actionable intelligence. This transforms OPA from being a simple gatekeeper to being the brains of our risk system. This brings us to our next pattern, connecting decisions to actions with cloud events. Our fast synchronous payment gateway should only do one thing, make a decision. Everything else, sending an SMS, updating a database, notifying a Slack channel, is slow and must happen out of the way. So our pattern is simple. When our Go service gets a decision from OPA, it looks at the actions in the metadata. For each action, it creates a standard cloud event following spec 1.0 and toss it onto our event bus. For example, if the action is freeze card, it published a card.frozen event. Downstream, our card management service can pick up that message and do the work of actually freezing the card. Another service might pick it up to send the user an alert. This pattern is critical. It keeps our gateway fast by separating the synchronous decision from the asynchronous workflow. We've talked about OPA unit tests. What about integration testing? How do you safely validate new policy behavior with 100% fidelity? We built what we call a policy sandbox, a service that consumes high-fidelity authorization data but doesn't impact any actual transactions. Following the same architecture as the real payment gateway, the sandbox runs the new policy in a predictive mode. Think of it like a parallel universe where we can test policy changes against production data without any risk. This is a simple UI our risk team use. They can enter some basic transaction information, and the sandbox makes a decision as if it were live, confirming the policy behaves exactly as designed. This validation is what allows us to confidently deploy the updated rule to production. It also assures our customers that their experience will be smooth and frictionless on the very first try. Our final pattern is what makes our system truly smart. It's about closing the loop and allowing our policies to learn from their outcomes. A policy shouldn't be a static rulebook. It should be a dynamic system that improves over time. Let's go back to that bank request. Flag an unusual purchase and ask the cardholder to confirm it. Here's how the feedback loop works. First, OPA flags it. OPA sees a transaction at a new merchant and asks the card and includes the notify user action in its decision. Second, the user responds. Our system sends a push notification, and the user taps, yes, this was me. Third, the system learns. That tap fires an event back into our system. An automated service hears this event and creates a temporary whitelist entry for that customer-merchant combination. Lastly, the policy adapts. The next time that same user shops at the same merchant, OPA sees the merchant on their safe list and approves the transaction instantly. No alert, no friction. This feedback loop allows the system to adapt to individual user behavior, all without a human having to manually rewrite a single line of policy. So after 3 years of running OPA in production, what have we learned? The benefits have been huge. We are more agile, our fraud detection is miles better, and our customers are happier. But it wasn't all easy. It's a new mindset for the whole team. Let me give you 2 examples. At first, we attempted single-round policy evaluation per transaction. There's no order of evaluation, also hard to override a specific rule. But we quickly realized that OPA evaluation is blazing fast. Multi-route calls have negligible performance impact. So we define a clear order of evaluation, say check tenant limit first, then MCC rules, then fraud, and so on. It allows precise rule override without affecting the entire policy set. Another example is that as Torpago has evolved from direct-to-business to bank-wide label solutions, we find that each bank partner has unique fraud rules and the transaction decline verbiage, making shared policy files complex and hard to maintain. So we create separate namespaces for each bank partner to avoid rule conflicts and to enable independent policy evolution. And that brings us to the future. We adopted OPA long before agent became a buzzword. Now we're exploring how AI could revolutionize policy management. Imagine a business analyst describing a rule in plain English and having all the regular code automatically generated for them. This leads to a fascinating idea. We call it Open Policy AI Agent, an autonomous system that could monitor policy performance, suggest improvements, and even implement them, with a human always in the loop for approval. That's the future we are building towards. So there you have it. Some key takeaways. OPA enables true separation of policy from code. Real-time policy evaluation is not only possible, but practical. And rich metadata transforms simple decisions into intelligent actions. But the real win, when that bank partner sends another message asking us to flag transactions at a new set of merchants, we can respond with give us 10 minutes. Thank you. Questions? Yeah.
So it sounds like you're using OPA here more as just a Go rules library.
Yeah.
Have you looked at other Go rules libraries? Was it OPA's performance, DSL that worked better for your case?
So the question is, have we looked at other library options for the rule evaluation? Yes, we look at other libraries, but I think OPA comes from a CNCF and also open source, and we compared with other models, and this library is the best, I think. Yeah.
There are different types of frauds, and I suppose OPA trying to address various frauds. Like it could be APP push limit frauds, it could be elimination attacks, etc. Does OPA implicitly take care of all of that? Because the patterns are really different based on different types of fraud.
Okay, so the question is how did OPA handle the other kinds of fraud patterns? Yeah. So I think the idea is OPA is just rules, and our Go service provides data. So if there are new pattern of fraud, we first look at the data and put that into input, and the OPA just write the rules, no matter what the input is. Yeah. For example, we are the frequent pattern we saw is same merchant fraud rule, like transactions. We repeated attempts at the same merchant during very short time frames. So you need an aggregation query to find how many transactions, what's the total volume of the transactions during that very short time window, and just give OPA the data. And you will decline the transaction when the input data will trigger the rule.
Okay, and that pattern analysis is done by separate model, not OPA itself, right?
Yeah, yeah. Question? Yeah.
Have you thought of using OPA for use cases such as sending money, receiving, or reconciliation?
So the question is, have we used OPA for other kinds of use cases like reconciliation? I think OPA is as most use cases I saw is for API gateway, like API authorization. You can define the specific authorization based on the HTTP path and the HTTP verb, like get, post, those things. That's the most common thing. Reconciliation, we haven't looked at that. Yeah.
Are you using AI-generated Torpago code in production?
Yes. Yeah. So it works really well. Cloud Code is so smart. 3 years ago, I had to hand write those rules. Now I just describe in English, and it generates and all the unit tests. Yeah.
Yeah, how well does it work with like aggregates? So let's say you had like a user daily spend limit of $1,000, right? So you're not looking at just one $50 transaction, but perhaps if there's 500, 550, and look like the aggregate amount of activities or given resource as opposed to just inline single transaction rules.
So the question is, how long did the aggregation query take?
Yeah, I would say you have the case where it's not just single transaction rules,
Yeah.
rules and like step limits or something like that.
Yeah, so we use Postgres. I think this performance is very fast. Right now, we have aggregation query for same merchant rule, and also a cheap fallback, like the recent cheap fallback if detected, and also if there's inactivity rule, like after a certain 90 days, there's no activity on the card. And there are not many aggregation query. I think the SQL query is pretty fast. Yeah.
Regarding your secret sauce,
Yeah.
I understand that OPA is stateless, but I see that you have implemented Postgres and you have dynamic additional logic in there. So that's part of the secret sauce that you guys have put like enhance OPA.
What question is about secret sauce?
Yeah, just so OPA has some features out of the box.
Yeah.
And I was just trying to follow up on your secret sauce when you mentioned that you have Postgres and dynamic rules to enhance OPA. So that's
Yeah, I think the question is about the patterns we develop to enhance OPA. Yeah. So I think my favorite part is the custom actions. So we decline transaction not just based on a rule itself, but also based on the action, because business logic changes very quickly. Sometimes when a rule is triggered, they say, I don't want to decline it. But above a certain threshold or in very specific MCC, business teams decline this transaction. So we can write different rules and with different actions. Some rule include the action like decline transaction. Some other rules don't include it. So when all of the rules will be triggered, and when any one of them include the action like decline transaction, the transaction will be declined. But if no such action, those rules will just trigger as an internal alert. So we know that, oh, some rules got violated, and we need to look at it. Maybe business team want to manually review it, and then give us feedback how we can improve the rules. But we use combination of rule, OPA rule itself, and the custom actions to keep up with the business request. Yeah. Any other questions? I think it's lunchtime. Yeah. Thank you. Thanks to Moov again and all the sponsors of this event. Yeah, thank you.